Let's look at this problem. This is actually from my dynamics video 31, not statics. So in this problem, we have this 20 kilogram uniform thin hollow square plate that is pinned at point O. Therefore, it can only rotate about point O, about this axis passing through point O, perpendicular to my screen. So at this instant, it is subjected to this external force, external couple moment, and it has angular velocity of 6 radian per second counterclockwise, and we need to determine its angular acceleration as well as the resultant force at pin support O. So for this type of problem, we always start with a free body diagram. So it's just a rough sketch. On the free body diagram, we have applied force, 100 Newton force right here, and we have the 80 Newton meter couple moment. But don't forget, we have weight force. So weight force is 20 kilogram times 9.81 meter per second squared. And then at point O, we have two unknowns components because we have a pin support here. Because this is a rotation about a fixed axis problem, so we, according to convention, we would draw our force in the normal direction as well as a tangential direction. So that completes the free body diagram, and then we also draw the kinetic diagram. Therefore, at point G, so this is a point G, we will have, so M A N M A T, that's the acceleration along the normal and tangential direction. And then we will also have IG alpha. IG is the mass moment of inertia about the gravitational center. So we have three unknowns we need to solve for. The first one is the alpha, and then ON and OT, because in order to determine the resultant force at the pin support point O, we need to solve for both of these components. And for this problem, we can write three equations as well. So let's write them out first. We can write resultant force along the normal direction, and that equals to ON plus the weight is also along the normal direction, 20 times 9.81. So that's all the forces along the normal direction, and that equals to MAN. But in this case, because this is a rotation about a fixed axis, this becomes M times omega square R. M is known as 20, omega is known as 6 squared, and then R is this distance right here from here to here. So if this square has a side of 0.4 meter, then this R right here equals to 0.4 times square root of 2 over 2. So from this equation, we realize that we only have one unknown, which is ON. So we can already solve for ON. And ON equals to 7.45 Newton. We can write another force equation, resultant force along the tangential direction. The total force along the tangential direction, that will be the 100 Newton applied force plus OT. And then this equals to MAT, which equals to M times alpha R. So M is known as 20. R is again 0.4 times the square root of 2 over 2, that's the radius. But alpha is another unknown. So this equation has two unknowns, OT and alpha. So inevitably we have to write another equation, which is going to be a moment equation. So we have options. We can either write resultant moment about point G, which is the gravitational center, equals to IG alpha, or we can write resultant moment about point O, which is the center of rotation, and that equals to IO alpha. And IO is the mass moment of inertia about point O. Either one will work. Normally, we would like to write this equation. The reason is because if we summarize the moment about point O, then two of our unknowns, OT, OM, they do not create moment about point O. Therefore, they do not show up in this moment equation. But if you use this equation instead, that will work as well. Anyway, we're going to summarize the moment about point O, which equals to the 80 Newton meter free couple moment and 100 Newton. This force has moment arm of also R, therefore 0.4 times square root of 2 over 2. That's the total moment about point O. The other three forces, the weight force, OT and ON, they do not create moment about point O because they have lines of action passing through point O. On the right hand side, this equals to IO alpha, which equals to IG plus MRG squared alpha. MRG are both known, so we need to determine IG. So this is a composite body, composite plate. It can be considered as a big solid square plate minus a smaller plate in the center, and they have the same center of gravity. So the big one has a mass of m1, the smaller one has a mass of m2. And because it's a uniform, meaning that the density has no variation, density is the same throughout. Therefore, their masses, the ratio between their masses is the same as the ratio between their areas. So this is a 4-to-1 ratio in their area. Therefore, M1 equals to 4 times M2. But at the same time, M1 minus M2 equals to 20 kilogram. So from there, we can solve for both M1 and M2. So M1 equals to 26.67 kilogram, and then M2 equals to 6.67 kilogram. Now, for a square thin plate, or actually a rectangular thin plate, if we draw it this way, to give this a three-dimensional look of it, if we're calculating its mass moment of inertia about this axis that is perpendicular to its surface passing through its gravitational center point G, then the equation, we can look up the equation in the book, and that is going to be 1/12 m a squared plus b squared. This is a square A, and this is B. So AB are the two sides of the rectangle. So for us, because we have squares, so we can easily tell that the mass moment of inertia about the axis passing through point G perpendicular to the screen for the big M1 plate is 1/12 M1 times 2 times L1 squared. Because remember before, it is A squared plus B squared. AB are the two sides. But because we have a square, therefore that's 2 times L1 squared. And the same thing for M2, we have 1/12 M2 times 2 times L2 squared. So substitute in the values. M1 is 26.67 kilogram. M2 is 6.67 kilogram. L1 is 0.4 meter, and L2 is half of that, 0.2 meter. So with all that, we can determine IG for this hollow square plate equals to 0. So basically 2/3 in the unit of kilogram meter squared. So that is IG, and then we substitute that in. This equals to 2/3 plus 20 times RG is the same, 0.4 times the square root of 2/2 square alpha. So in this third equation, this moment equation, realize that this can be completely evaluated. On the right hand side, we only have one unknown, which is alpha. So from here, we can already solve for alpha. So alpha equals to 47.8 radian per second squared. substitute the alpha value into this second equation, we can solve for OT to be 107.2 Newton. And then we already know ON is 7.45 Newton. Therefore, the total force O equals to the square root of ON squared plus OT squared. And because you can tell that ON is very small when compared to OT, so this eventually is 170.4 Newton. If you are keeping three significant figures, that's actually simply 170 dot Newton. So that will be the final answer for this problem.